So here's the system redrawn for the center of mass frame and a perfectly elastic collision. So what did we have? We've got M1 moving at 2 meters per second, which is positive, in other words, to the right. M2, which is moving at negative 3 meters per second. So what does that actually mean? What's the actual motion look like? Well, that means that M2 is moving to the right. So it's moving to the right at 3 meters per second. In other words, U is negative 3 meters per second. That's the initial situation. And then the final situation, we've got M1 with U is negative 2 meters per second. So what does that mean? That actually means that M1 is now moving to the left at 2 meters per second. And then M2 has U2 at 3 meters per second. Let's just compare these initially and finally. What's happening to M1? It comes in at 2 meters per second, collides, and then bounces back at 2 meters per second. In at 2 and then out at 2. So it's just going in and bouncing back at exactly the same speed both ways. What is M2 doing? It is going in at 3 meters per second and then bouncing back out at 3 meters per second. So it's coming in at 3 and then bouncing exactly back at 3. Very interesting, very symmetrical, we might say. So let's calculate what the total initial momentum is, just like we did for the initial frame that we were considering when we had both objects moving to the right and we calculated the total momentum. Let's do the same here. And what do we get? So we get the total initial momentum will be the momentum of mass 1 initially plus the momentum of mass 2 initially, which will be 6 kilograms times 2 meters per second plus 4 kilograms times, now we've got to keep that minus sign because that is indicating the direction because U is a vector, but P is also a vector, so we've got to maintain that negative sign in here. So times negative 3 meters per second. And what do we get? We get 6 times 2, 12 kilogram meters per second, plus 4 times negative 3, that's negative 12 kilogram meters per second. 12 plus negative 12, we get 0. The total initial momentum in the center of mass frame. I should emphasize that. Let's write that down. This is the center of mass frame. So in the center of mass frame, our total momentum is 0. That's going to be a very consistent result. Anytime we look at a collision in the center of mass frame, that basically means in a frame where the total momentum is 0. That is essentially what the center of mass frame means. We subtract off the velocity of the center of mass and we get into a frame where the total momentum is 0. Okay, so there we go. Let's look at the velocity of the center of mass. What's the velocity of the center of mass in the center of mass frame? Well, the same result holds. The velocity of the center of mass is equal to the total inertia divided by m, but that's going to be what? 0 over the total mass, and that is 0. In other words, the center of mass is stationary, which we might have guessed. In the center of mass frame, the center of mass is not moving. It's stationary. Okay, well, that's not a big surprise. Let's look at the kinetic energy. Now, what kinetic energy is this that we would look at? The kinetic energy of the sum of these two. We're looking at the kinetic energy in the center of mass frame, which is essentially the kinetic energy relative to the center of mass. When we were looking at the kinetic energy earlier, we looked at the total kinetic energy. We just summed up 1/2 mv squared for both masses. That was the total kinetic energy. But then we looked at the kinetic energy of the center of mass. In other words, how much energy did the motion of the center of mass contribute? And we calculated that. And we got a value that was less than the total. We're now going to look at the kinetic energy in the center of mass frame, I should say, which is basically giving us the kinetic energy relative to the center of mass. I'll come back to that in just a minute. What do we get? So this is, I'm going to call this the relative kinetic energy, and we're looking at it initially. So what's that? That is equal to 1/2 m1 whoops, sorry, that's a habit, u1 initial squared. So we're now using the u velocities, the velocities relative to the center of mass, which is why we call this the relative kinetic energy, as opposed to v, and then plus 1/2 m2 u2 initial squared. And what do we get in that case? So we'll get 1/2 times m1 is 6 kilograms, times u1, which is 2 meters per second, squared, plus 1/2 times m2, which is 4 kilograms, times u2 initial, which is -3 meters per second, squared. Now notice, it doesn't matter whether this is positive or negative. When we square it, we're going to get a positive number. So the kinetic energy does not depend on the direction of the motion. Motion this way, positive kinetic energy. Motion this way, positive kinetic energy. Kinetic energy is a scalar, it's not a vector. The direction doesn't matter. Then what do we get? So we multiply this out, and we get 1/2 6 times 2 squared, that gives us 12 joules. And then 1/2 times 4 times -3 squared, or +3 squared, that gives us 18 joules. Giving us a total of 12 plus 18, or 30 joules. Okay, great. Now, what I want us to remember, a couple things that we calculated in the general case. Remember the total kinetic energy initially for the situation in the general frame, when we first started looking at it, not the center of mass frame, that was 210 joules. We found then that the kinetic energy of the center of mass, the 1/2 times the total mass times the velocity of the center of mass, that was 180 joules. And this was initially. And what do we have now? We've got the relative kinetic energy initially is 30 joules. What do we notice? The total kinetic energy is equal to the kinetic energy of the center of mass plus the relative kinetic energy. And we're just looking at this initially. So the 210 equals 180 plus 30. What does this mean? Give me 1 second. What does this mean? It means that we can think of the kinetic energy as being broken into 2 parts. We've got some general motion that looks like this. And we determine the kinetic energy, the total kinetic energy. In other words, the kinetic energy of mass 1, kinetic energy of mass 2. That's the total kinetic energy. We can think of that in 2 parts. First, we can think of, imagine watching the whole thing taking place in a frame that's going along with the objects in the center of mass frame. So imagine I'm walking along in the center of mass frame. To me, the masses look like they're just going like this, coming together, and then moving apart. The motion of the whole system in terms of the motion of the center of mass, that's what this part is, the kinetic energy of the center of mass. Thinking of the system as basically a whole. But then we have the kinetic energy basically in the center of mass frame, which just looks like this, which is the motion that is relative to the center of mass. So what does the motion look like in the center of mass frame? That's this part, with no total overall sideways motion. Okay, so that's kind of what we're showing right here. The total initial kinetic energy is equal to the kinetic energy of the whole system as a whole moving, and then the motion of each of the parts moving relative to the system. Okay, very, very good. One more thing I want us to notice. What is that relative velocity in terms of the center of mass frame? What is not vrel, but now urel? What is urel initially? Well, that is equal to, just like we defined it before, it'll be u2 initial minus u1 initial, which in this case, u2 initial is -3 meters per second, minus u1 initial, which is 2 meters per second. Negative 3 minus 2 is negative 5 meters per second. But that is exactly what we got for VREL initial. So, the relative velocity, which means the velocity of the two objects approaching each other, how rapidly they're actually coming together, is the same whether we look at it in the general frame or if we look at it in the center of mass frame. The speed at which they approach is the same. But that makes sense because the way we found the u values was basically just to take the v values and subtract the velocity of the center of mass. If we subtract the same number from both u1 and u2, from both v1 and v2, the difference is still going to be the same. So that makes sense. The fact that urel gives us the same value as vrel initially, that makes sense. Okay, great. Let's clean this up a bit. I'll put all of the values that we calculated initially over there, and then let's do the same thing for the final situation. We found, to summarize, total initial momentum equals 0. Velocity to the center of mass equals 0. The relative kinetic energy is 30 joules. And the relative velocity between the two is negative 5 meters. And let's keep in mind, this is for the center of mass frame. Let's do those calculations for the final situation. And what do we have? We have the total final momentum will be the sum of the final momenta, P1 final plus P2 final, which will be m times u. So we'll have, for mass 1, we'll have 6 kilograms, times u1 final, which is negative 2 meters per second, and then plus m2, 4 kilograms, times u2 final, 3 meters per second, which leaves us with 6 times negative 2, negative 12 kilogram meters per second, plus 4 times 3, 12 kilograms meters per second. So negative 12 plus 12, 0. Again, we have the total final momentum equal to the total initial momentum. What's the velocity of the center of mass going to be finally? Well, I think you can see, again, 0 divided by the total mass is going to be 0. So, again, the final center of mass is still stationary. It's not moving. We might have guessed that. What is the final relative kinetic energy? Vk rel final. That's going to be 1/2, I won't write each term out, 1/2 m1 u1 final squared plus 1/2 m2 u2 final squared. What's that going to give us? 1/2 times m1, 6 kilograms, times u1 final, negative 2 meters per second, squared plus 1/2 times m2, 4 kilograms, times u2 final squared, 3 meters per second squared. And what do we get? We get 1/2 times 6 is 3, times 4 is 12 joules, plus 1/2 times 4 is 2, 3 squared 9, 2 times 9, 18, 18 joules, 12 joules plus 18 joules, 30 joules. Again, equal to our relative initial kinetic energy. Now, that is because we are looking at an elastic collision. Remember, we said that in an elastic collision, energy is conserved. We are assuming the internal forces acting between M1 and M2 are conservative forces, and so, what does that mean? Energy is conserved, and in particular, in this case, kinetic energy is conserved. So, whatever kinetic energy we start with is equal to the kinetic energy we end up with. Okay, and then what is our final urel? Urel final. That's going to be u2 final, which is 3 meters per second. Whoops, sorry. Yeah, that's right. We'll take u2 final first. So 3 meters per second minus u1 final, which is negative 2 meters per second. We have 5 minus negative 3, which is 3 minus negative 2, which is 3 plus 2, or 5 meters per second. And what do we notice? We end up with the negative relative velocity that we started with, which again, that makes sense. What does this mean? It means that the speed that the masses come in with, which is negative initially, is the same speed, relative speed, that they go out with after the collision. But in this case, though, the M2 is moving faster, so it'll be a little bit like this. Coming in, this one's coming faster, bounces out, this one, M1 goes out slower, M2 goes out faster. Okay, very, very good. Excellent. Now, so far we have been looking at an elastic collision, one where the kinetic energy is conserved. Well, what happens if the internal forces are not conservative? What's going to happen then? Let's go back to a general situation for a second. Let me just draw something down and let's think about that.